Hello. In today's experiment, we will measure the specific heats of copper and aluminum using the principle of method of mixtures. Well, I will review the theory of this along with the method. Alright, now if you read the instructions I gave you, the procedure goes like this. Measure the mass of the given piece of copper. In fact, I have 5 samples of copper and 5 samples of aluminum. So you will be working with each piece. So let's take first the first piece of copper and describe the method, and the method will be the same for all the other pieces. Measure the mass of the first piece of copper and record it as M1. So let's use the same method here. We say mass of the first piece of copper. I'm going to call it mass of copper 1. The first piece we call it M1, and always remember the units in proper units. Kilogram. I will not write units here. What is the next thing to do? Keep the solid in boiling water. So once the mass is measured, you will keep that solid in boiling water so that it is heated to a high temperature. Measure the mass of the calorimeter. Well, a calorimeter is this. We will be using this. Measure the mass of the calorimeter and record it as M3 kilogram. So you have mass of calorimeter is M3. And then measure 80 milliliter of water into the calorimeter and measure the combined mass of calorimeter and water. So this time you have mass of calorimeter plus 80 milliliter of water, and we call that M2. And what is the next thing to do? Measure the temperature. What is the initial temperature of the calorimeter and water? So we have a initial temperature of calorimeter and water. I hope you can read my writing. The initial temperature of calorimeter and water, let's call it 31 degrees Celsius. And what is the next step? Measure the temperature of boiling water. That is the temperature of the hot solid. Temperature of the hot solid. We will call that 32 degrees Celsius. Okay, so we take a solid of mass M1, heat at a temperature 31 and heat it to a temperature 32. What we are now going to do is that hot solid at this temperature is now going to be transferred to this calorimeter that contains this water, and then measure the equilibrium temperature. Okay, so carefully transfer the solid from the boiling water into the calorimeter, making sure that no hot water is sticking to the solid, and the transfer must be done very carefully and quickly to avoid heat loss in the process. Alright, what is the next measurement that you will be taking? Close the calorimeter, stir the contents and measure the equilibrium temperature recorded, theta 3. Measure the final equilibrium temperature. The final equilibrium temperature will be 33 degrees Celsius. Okay. Now you have practically all the measurements you have. Is that right? And you will be doing these measurements using each of the pieces. Well, you don't need to measure the calorimeter all the time. Once you have measured once, that will remain a constant. And also the mass of calorimeter plus water. We are taking 80 milliliter of water every time. That means that M2 will remain a constant. Now, what is the mass of water alone? The mass of water alone is M2 minus M3. Is that right? Okay. Mass of water alone is M2 minus M3. Now, what is the process happening here? The process is the hot solid will lose heat and the cold water and calorimeter will gain heat. Now, what is the principle of method of mixtures? When you mix cold objects with hot objects, the amount of heat lost by hot objects will be equal to the amount of heat gained by the cold objects. That is the principle of method of mixtures. And you should also know from theory class that the quantity of heat gained or lost by an object is given by mass times specific heat times the change in temperature. Alright, now once you have that, I'm going to now take off each step from above and write down my next step. What will be my next step? Well, tell me, what are the things that absorb heat in this experiment? The calorimeter will absorb heat. Water also will absorb heat. Alright, let's write down those quantities. What is the heat absorbed by calorimeter? I'm going to write that at the top. Heat absorbed by calorimeter, or we say heat gained by calorimeter. Well, heat gained or lost by an object is mass times specific heat times the change in temperature. Now, the calorimeter is actually aluminum, and I have given you the specific heat of aluminum in here. That is 921 joules per kilogram per Kelvin. So what is the heat gained by calorimeter? Its mass, which is M3, the calorimeter mass is M3, multiplied by the specific heat is 921 joules per kilogram per Kelvin. And the change in temperature, what is the change in temperature of the calorimeter? It started off with an initial temperature of theta 1, and the final equilibrium temperature is theta 3. So the change in temperature is theta 3 minus theta 1. Alright? Heat is also gained by water. What is the heat gained by water? Heat gained by water is the mass of water. What is the mass of water? The mass of calorimeter plus water is M2. The mass of calorimeter alone is M3. Therefore, the mass of water alone is M2 minus M3. That is mass of water. And the specific heat of water is 4180 joules per kilogram per Kelvin. So mass of water times the specific heat of water times the change in temperature. Tell me, what is the change in temperature of water? The initial temperature of water is theta 1. The final equilibrium temperature is theta 3. Therefore, the change in temperature is theta 3 minus theta 1. Alright, now let me take off these. What is therefore the total heat gained? Calorimeter gained heat, water gained heat. So the total heat gained is the sum of these two. Total heat gained is add these two. And I'm going to take theta 3 minus theta 1 as the common factor. That will give me 4180 times M2 minus M3, that is this quantity, plus 921 M3, and multiply that quantity by the change in temperature, theta 3 minus theta 1. That is the total amount of heat gained by calorimeter and water. And who is losing heat? The hot solid. What is the amount of heat lost by the hot solid? Heat lost by hot solid, alright, is the mass of solid times the specific heat of solid times its change in temperature. What is the mass of the solid? We measured the mass of the solid and called it M1, if you remember. So the heat lost by hot solid will be M1 times specific heat of that solid C, we want to measure it, times the change in temperature. The solid has been heated to a temperature, high temperature theta 2, and the equilibrium temperature is theta 3. Therefore, the change in temperature is theta 2 minus theta 3. Okay, and now we say the amount of heat lost by the hot solid, that is this quantity, is equal to the amount of heat gained by calorimeter and water. And that is the principle of method of mixtures. So we have M1C times theta 2 minus theta 3 equal to 4180 times M2 minus M3 plus 921 M3, all multiplied by theta 3 minus theta 1. Well, that is the equation for our lab today. And as I said, we will be doing the lab for two materials. One is copper and the other is aluminum. So what are the variables here? If you look at this, the variables are, well, theta 2 minus theta 3 will change. Theta 3 minus theta 1 will change. Look at these quantities. You know that every time we take 80 milliliter of water, that means the mass of water is a constant. M2 minus M3, that is a constant. The M3, the mass of calorimeter, is a constant. That means all these quantities are constant. Now, M1 is going to change because we got 5 samples. So when you use sample 1, if that is M1, sample 2, M1 will change. So sample 3, sample 4, and sample 5, the mass of the solid is going to change. We are going to, for each material that is aluminum, we are going to use 5 samples. Now, depending on the sample, this M1 will change. And when M1 changes, the temperatures will change. So those are the variables. How will you write this equation in the form y equal to mx? When you change the mass of the solid, the temperature will change. So what we're going to do is we're going to solve for, watch how I'm going to do that. Theta 2 minus theta 3 divided by theta 3 minus theta 1. We're going to obtain this ratio. Let me write that down a little more neatly. Theta 2 minus theta 3 divided by theta 3 minus theta 1. That is the falling temperature of the solid divided by the gain in temperature of calorimeter and water. That temperature ratio will be equal to what? Will be equal to 4,180 times, well, M2 minus M3 plus 921 M3. Alright, now this is going to be the quantity out here. Alright, we divided this over here. So this will now be, this quantity M1C will come on the denominator. So this will be over C times 1 over M1. Did you understand that? Well, it will be times 1 over M1. In other words, if this is your Y, then this will be your X. 1 over M1 will be your X. And all this quantity is a constant. So if you draw a graph of this temperature ratio on the y-axis and 1 over m1 on the x-axis, the slope of that graph will be this quantity. And when you measure the slope, make it equal to this quantity and then solve for C. Alright? So you do it for copper and aluminum. That means there will be two graphs and you will get two values of the specific heat. I hope you understood the method. And now, when I do the experiment, you need to take the measurements and do the tabulation. Alright? If you tabulate your values, it should look more or less like this. You start with copper, mass of calorimeter plus water, and therefore mass of water alone, where these things will not change because we are taking the same quantity of water every time. The initial temperature of the calorimeter and water, that is the room temperature, which you can measure. The final temperature of the hot solid, which is the temperature of boiling water. So all these are going to be known in the beginning. And now you have 5 pieces of copper. Now I'm going to give you the 5 pieces of copper and you are going to measure the masses. You can enter them here, sample 1, sample 2, sample 3, and then I will heat each of them to a temperature theta 3, which, I will heat them all to a temperature theta 2 and then transfer them to the calorimeter, and you need to measure that temperature theta 3. Then obtain the fall in temperature of the solid, the rise in temperature of calorimeter and water, and calculate the ratio of that temperature. Then calculate the reciprocal of the mass. Okay, let's now measure the masses of the 5 pieces of copper. Well, this is sample 1, measure its mass and record it. So when I next time refer as sample 1, this will be the one I'm talking about. So measure its mass and record it. Alright, sample 2, that is sample 2. Okay. Sample 3 is this. Alright. Sample 4 is this. Alright. Sample 5, look at this. It's these copper balls. Now, how do I measure the mass of these copper balls? Well, I don't know. I'm going to ask you to measure it. Now, I'm going to put this container in there and find the mass of that container. And now I'm going to put all these copper balls into that container. And now measure the combined mass. And from the two measurements, obtain the mass of these copper balls, or whatever you want to call it. This is your sample 5. Alright? So don't forget about these samples. You have now the masses of all the 5 samples. Before we proceed further with copper, let's also measure the mass of the aluminum samples. Alright? The first aluminum sample is this. Write down its mass. The mass of the first aluminum sample. Alright? Alright, the second sample for aluminum. Okay. Sample 3 for aluminum. That's the aluminum ball. That's the sample 3. Okay. Sample 4 for aluminum. And finally, sample 5 for aluminum. So you have the mass M1 for 5 samples each for copper and aluminum. So you have the M1 values for copper and also for aluminum. So you can now start making the table for aluminum. Alright? And you can obtain these values, and then we need to heat the solid to a high temperature and mix them together and measure the equilibrium temperature. That's our next task. Before we start with a sample, let's measure the mass of the calorimeter M3, the mass of the calorimeter plus 80 milliliter of water. So we will get M3, M2, and measure the room temperature theta 1. Okay, let's do that first. Before you start using the scale, look at the least count of the scale. This is 0.00. So that's a whole number and you have 2 decimal places. So the least count is 0.01. You can measure mass up to 0.01 gram there. And let's now measure the mass of this calorimeter. I'm cleaning the calorimeter, make sure that it is dry. Alright. Measure the mass of this calorimeter, that is your M3. And now I'm going to put 80 milliliter of water in it and measure the mass again. I have a beaker here that can measure exactly 80 milliliter, and I'm going to take 80 milliliter of water into it. Alright. I think I have exactly 80 milliliter of water, and I'm going to put that in the calorimeter. Measure that mass. This is your M2. So you got your M1 and M2. I hope when you read it, you understand that the last two digits are the decimals. Is that right? This is correct to a 100th place. So read it correctly. You got M1, M2, and now I want you to read the temperature. The room temperature, theta1. Now read this temperature measure, and this is your room temperature, theta1. So whenever you want the value of theta1, this is your theta1. I hope you can read the thermometer well. That is -10, 0, 10, 20, 30, 40, and so on. So read the temperature theta1. Well, as you can see, there is a good cooking session going on here. I have all the samples in water which is boiling, and I want you to measure the temperature of the hot water. Now this will be the hot temperature theta2 for all our samples. Alright, I'm going to move the camera so that you can take the temperature. Alright. Okay, measure the temperature, that is your theta2. Measure that temperature and record it as theta2. Alright? Okay. We will now work with the first copper sample. Now, I have put the calorimeter inside a case so that it is insulated. I'm now going to transfer the first copper sample. Now, you know the mass of the first sample we had measured. I'm going to transfer the first copper sample to the water, and we need to measure theta3. Is that right? Okay. Now, I need to do that very quickly without heat getting lost. Now, there we have, and I want you to measure the final temperature. Alright, I have now transferred the first sample of copper, and now measure the temperature. Well, you've got to wait for the temperature to get steady. The temperature is increasing now. Wait for the temperature to become steady and measure that temperature. Alright, this is the first copper sample. Measure this temperature and record it as, what would that be? Theta3 for the first copper sample. I think the temperature is now steady. You can take that measure. Got to wait for about a couple of minutes to make it steady. We will now repeat this for the second copper sample, and there it comes. You need to now look for the equilibrium temperature. Alright, that is the second copper sample. Look for the equilibrium temperature. Alright, I think the temperature was steady, is now decreasing. So that is 33 for the second copper sample. We will now repeat the experiment for the third copper sample, and I'm going to bring it quickly. There we are. Okay, and look for the temperature. Wait for the temperature to become steady. Try and read the temperature as best as you can, to the nearest tenth if you can. So you can make a guess and read it to the nearest tenth. Alright, look for the maximum temperature, that is the equilibrium temperature, and read it. I think it has now reached the maximum temperature, is that right? Okay, now it is coming down. Okay, so that's the theta 3 for sample 3 of copper. Let's now repeat it for sample 4 of copper. Sample 4 of copper, there we have. Alright, watch the temperature. Alright, look for the equilibrium temperature there. I think we have the equilibrium. In fact, it is coming down. Try and read it correct to the 10th place. Okay, that is 33 for sample 4 of copper. We will now repeat the experiment for sample 5. Now sample 5 has been heated in a container there, and I'm going to drop it into the water there and measure the equilibrium temperature in there. Alright, wait for the temperature to become steady. Okay, those are the small copper balls. Wait for it to become steady and measure it correct to a 10th place as best as you can. Alright, I think it has reached the equilibrium, and take the measurements now. That is theta 3 for sample 5 of copper. We are now ready to start with the aluminum samples, and we will start with the first sample. The first sample of aluminum, let's go. Alright. Try and measure the equilibrium temperature there. That is the first sample of aluminum. Try and measure the temperature to the 10th as best as possible. Okay, I think it has reached the equilibrium temperature. That is theta 3 for sample 1 of aluminum. Okay, we are now ready to start the second aluminum sample, and here I bring it. That is the second aluminum sample, and try and measure the temperature as best as you can. Alright, I think it is reaching steady state, equilibrium temperature. You can take that measurement. Okay, that is 33 for sample 2 of aluminum. We will now repeat the process for sample 3 of aluminum. Okay, let's work with sample 3 of aluminum. There it goes. That's sample 3, and look for the equilibrium temperature. Alright, I think it's now equilibrium, is that right? Okay. Alright, measure that temperature, and that is 33 for sample 3 of aluminum. Let's now work with sample 4 of aluminum, and here comes sample 4. Okay, and look for the equilibrium temperature. Alright, try and read it as accurately as you can to the nearest tenth. I know the alcohol level is hiding behind 30, but you can find its exact position. Okay, that is 33 for sample 4 of aluminum. Okay, there we go. And now we are ready for sample 5 of aluminum, and let's bring it over. There you have sample 5. Well, measure that temperature to the nearest tenth when it becomes steady. And I think it has become steady now. All right, we have now finished with all the samples. So in your report you must have a separate table and a separate graph for copper and aluminum. Now, this lab is the assessment lab. Those who did Physics 1 knows that we use one of the labs to assess your writing skills, your critical thinking skills, your application and analysis skills, your mathematical skills, your ability to organize and present a good report, your computer skills. All these are important skills we want our students to develop. So this lab or this lab report will be used to assess these skills. And therefore, you must give me 2 copies of the report. The one used for assessment must contain only your ID number. It is not used for assessing individual students. It is used to assess the whole program. You understand that? It's to assess how effective the program is in instilling these qualities and skills to our students. So this will not be an individual assessment. Okay, so send me 2 copies, one for normal grading and the other for assessment. All right, answer all the questions, and if you have any difficulties, let me know. I will see you for the next lab later on.